In this video, we will learn about the conjugate root theorem and how it can be used to solve polynomial equations. From the previous video, we have learned how to solve quadratic equations for complex roots. For example, these two equations can be solved to give the corresponding roots. And one thing we can note is that the roots always occur in conjugate pairs. But is this always the case? If, for example, we solve other polynomials where the coefficients contain imaginary terms like this, we will find that the roots after solving using the quadratic formula will not be in conjugate pairs as shown over here. So what we can observe is that if and only if all the coefficients of the polynomial are real, then we will be able to get conjugate pairs of roots. In other words, if we have a plus bi as a root of a polynomial, and we see that all coefficients of this polynomial are real, then a minus bi must be another root of the polynomial. This is the conjugate root theorem. In example 1, we have this cubic equation and we are told that minus 1 plus I is the root of the equation. And we are going to make use of it to determine the other two roots. So first thing to note is that all the coefficients of our cubic equation are real numbers. Therefore, the conjugate of minus 1 plus I must be another root. So we can say that since all coefficients are real, minus 1 minus I must be another root. Next, we want to find out the third root, and this third root must be a real number because the first two roots have already formed a conjugate pair and there is no other root for this third root to form another conjugate pair with. So with that, we can say that this equation z cubed minus 2z minus 4 can be factorized into z minus 1 plus I multiplied by z minus negative 1 minus I multiplied by z minus a, where a is the third root that we are required to find. So we can simplify this equation first by combining the first two terms to get z squared plus 2z plus 2 multiplied by z minus a. So since we know that these two expressions are equivalent, we can do a comparing coefficient. And therefore, we can say that by comparing the coefficients of the constant, which is z power 0, negative 4 must be equals to negative 2a, and therefore we get a equals to 2. And we can conclude by saying that the other two roots are z equals to minus 1 minus I and z equals to 2. Example 2 looks very similar to example 1, but one thing we have to note is that the coefficients of our cubic equation now are not all real numbers, as seen in our coefficient of z squared and z. Therefore, we cannot apply the conjugate root theorem to say that z equals to minus I is another root. So this is one thing to take note. Don't always assume that we can always apply the conjugate root theorem. Always check the coefficients of the polynomial. So we have to make use of another way to solve for this equation. What we can do is to try to factorize this original expression, 1 minus 3iz squared minus 2 plus 3i times z minus 2 must be equals to z minus I. So we have z minus the first root multiplied by a second term, which we can let it be a quadratic term. And this quadratic term is going to be z squared plus az plus b. A and b can be complex numbers, and the coefficient of z squared can be 1 because I know that when I expand it to get the z cubed term, it will be exactly the same as on the left hand side. So I've saved some trouble in determining one more unknown constant for the coefficient of z squared. And based on this, I can do a compare coefficient. If I compare the coefficients of z power 0, which is the constant term, I get negative 2 equals to negative ib, which can be simplified into b equals to 2 over I or negative 2i. Next, I will compare the coefficients of z squared, and they will give me 1 minus 3i equals to a minus I. And with this, I can solve for a to be 1 minus 2i. And thus, I can say that this cubic equation can be written as z minus I, z squared plus 1 minus 2i times z minus 2i equals to 0. And for me to solve this equation, I will have to factorize this quadratic equation over here, which luckily isn't too difficult. I can solve it to be z minus 2i multiplied by z plus 1. And thus, this cubic equation has been factorized into this form over here. And we can easily say that the other two roots are z equals to 2i and z equals to minus 1.